Tropical cyclones are responsible for over 700,000 deaths and $1.4 trillion in economic losses over the last half-century. For the agencies tracking these systems, every hour of advance warning directly translates into lives and infrastructure saved. Google DeepMind's new WeatherNext Cyclones model claims to provide an extra day of warming. Specifically, DeepMind reports that the model's 3-day forecasts are as accurate as the 2-day forecasts provided by previous state-of-the-art systems. Meteorological records from the last 20 years show that gaining a single day of lead time usually takes a decade of research. This model aims to deliver that improvement in one release. The deployment method is a significant departure from tradition. DeepMind has open-sourced the code and the model weights, making the entire system available for anyone to download from GitHub. This represents a sharp reduction in the hardware required for high-end forecasting. Prediction is moving away from massive physics clusters and toward individual AI accelerators. A 15-day WeatherNext forecast can run on a single TPU in less than a minute. Because this compute is now cheap and accessible, it is no longer the primary bottleneck in the forecasting pipeline. The defining technical puzzle isn't the model's accuracy, it is the fact that this accuracy exists despite the model being physically unable to see the hurricane's core. Meteorology is entering a period where the primary constraint is no longer generating the forecast, but rigorously verifying how an unexplained AI actually arrives at its answers. Measured against the ECMWF-ENS standard, WeatherNext maintains a position error of around 100 kilometers at the 3-day mark. In terms of intensity, the model reports an error of around 11 knots, outperforming HWRF, the US model built specifically to handle intensity. This performance was built on a massive scale of information. The model was trained end-to-end on nearly 20 terabytes of global atmospheric data. It also incorporated the IBTrACS database, which contains historical records for nearly 5,000 individual storms. Instead of producing one single path, the model uses functional generative networks to create a 1,000-member ensemble to map probability. A full 15-day forecast for all 1,000 of these ensemble members is generated from scratch in under 60 seconds. Subscribe if you want deep-dive analyses of open-source models the day they are released. With this level of speed and ensemble depth, forecasters can move past tracking a single likely path and begin mapping every possible devastating tail risk in real time. There is a basic rule in meteorology. A cyclone's intensity is driven by localized inner core thermodynamics. This process is dictated by the integrity of the eye wall and specific convective bursts. These highly volatile microscale physics and convective bursts occur rapidly at a tight range of just a few kilometers. Physics models like HWRF were developed for this specific reason. Global models were historically too coarse to resolve these core dynamics. This makes WeatherNext's technical requirements surprising. It only needs data at a 28 by 28 kilometer spatial resolution. That resolution is 100 times coarser than traditional specialized models. At 28 kilometers per pixel, the model cannot physically see the structures that dictate intensity. One possibility is that large-scale environmental fields, like ocean heat and wind shear, carry more intensity data than human researchers previously believed. The alternative is that the model is simply exploiting statistical regularities found in the 5,000 historical storms in its training record. DeepMind admits they don't know the answer yet. It remains an open research question how a model at this resolution produces such accurate intensity predictions. The claim that WeatherNext beats the state-of-the-art requires a look at how the data was calculated. The model switches its baseline depending on the metric. Track error was compared against the European ensemble, but intensity was compared against the US regional model. The paper does not show a single physics-based model losing to WeatherNext on every metric at the same time. The evaluation was also retrospective, focused on archived storms from 2023 and 2024. These archived storms share the same statistical distribution as the 5,000 storms the model used for training. Testing against historical outcomes is not the same as a live adversarial forecast. Statistical shortcuts often look like genuine physical skill in retrospective testing. An unexplained model may fail silently the moment it encounters a storm that behaves unlike anything in its training data. Operational policy is clear. Evacuation orders are not issued based on an unexplained AI. In practice, the model serves as an opinion generator for human forecasters to use alongside traditional physics suites. The model has already been used in the field. It helped the National Hurricane Center predict the rapid intensification of Hurricane Melissa in 2025. This is a single success. The burden of validation remains on anyone choosing to build on these open weights. The definitive live-fire test will be the 2026 Atlantic season. The National Hurricane Center will score the model prospectively against real-world events as they happen. If the model maintains its accuracy during this season, the traditional resolution limits of physics-based models will be invalidated. If the performance regresses toward the physics baseline, it will prove the retrospective was flattering. Either way, AI has forced physics-based forecasting into its most rigorous trial yet.